welcome back to the York County History Center. It's nice to see you all in person. This is our first, I'll mess with that in a minute. This is our first second Saturday in person for quite some time, and it's good to see you all here. Before we get started, do want to go over a few announcements. Our Civil War Roundtable is May 19th, and they'll be discussing baseball during the Civil War. May 25th is our early American cooking demonstration at the Colonial Complex. All Vets is May 26th with Brenda Webb, who is an Army, we're talking about Army Field Communications. The Friends Spring Luncheon is June 15th. We'll also be celebrating Juneteenth on June 19th. We'll have two exhibits, one of which is actually on display right now with the Emancipation Proclamation, which is in the lobby. And there will also be an exhibit by Ophelia Chambliss called Essential Pieces, an Inclusive Timeline of York County History. And our next second Saturday will be on June 12th with Adriel Resch, who will be talking about Etta Shining, the first Jewish woman in York. But today's presentation is by Stephen H. Smith, who I feel almost doesn't need any introduction at all because it seems all of you know him. But he writes about local history and authored award-winning family history, The Barshingers in America. He's a retired manager of design engineering at York International Corporation, is a registered professional engineer in Pennsylvania, and graduated from Penn State University with a master's degree in mechanical engineering. Stephen has been sharing York County history via the blog York's Past since 2012, and it contains over 1,140 posts, which is a lot. So without further ado, I will let Stephen present on his topic, the innovations of the S. Morgan Smith Company.
Thank you. Welcome, everybody. It's good to have people in person in these presentations. This presentation will focus on technological advances coupled with a little bit of the history of the company and showcasing some of the okay, now the speaker's on. And showcasing some of the lesser-known products that S. Morgan Smith made. And essentially, this talk. A better name for this talk, I think the mic might be a little high. You think so? Mic might be a little high.
Okay, sure.
Okay, testing. Okay, can everybody hear me now? Okay, good. Another way to word this talk is from water wheels manufactured by the S. Morgan Smith Company in York to turbines and more is another way to describe this lecture. Up front, I'll give a brief water wheel era introduction, progressing through hydroelectric turbines, and later on introduce you to a few other of their innovative products. This is one of S. Morgan Smith's maker's plates, which they have fixed to their products. And this is probably from one of the products they made in the early 1900s, or it might have even been a fixed product made in the late 1800s. Now, acknowledging some of the sources, the York County History Center is the source for the majority of the photos in this presentation. Newspapers.com was heavily used, along with a vast online collection of books, trade publications, company reports, and other things made available and searchable by Google and others. The photos are also discovered at Hagley Library and Archives in Delaware and at the Library of Congress. Some material came from my collections gathered around York County businesses. Reinventing the Wheel, who the author is back here, Stephen Nicholas, is also another resource. So after Christine Cooper asked me last October to present on this topic, I contacted Stephen Nicholas. Steve, with Terry Downs, wrote the excellent book, Reinventing the Wheel, The Incredible Story of S. Morgan Smith, Minister, Inventor, Industrialist. This fall, an article by Steve Nicholas will be coming out about S. Morgan Smith innovation, the wind turbine, which I've sidestepped during this talk. So look forward to that article in the journal coming out this fall. And the book is available out here in the gift shop in case you're interested. It was for a second Saturday program in 2017 where Steve Nicholas presented the fascinating story of the man, S. Morgan Smith. My presentation focuses on innovations of the S. Morgan Smith Company, and as one of his legacies continues through the leadership of his children and grandchildren. I also go beyond it and talk a little bit about the York County companies which that company basically branched off into. Voith Hydro, American Hydro, Precision Components, and Precision Calibration and Testing. I'll begin with a little concise summary of the earliest years of the S. Morgan Smith Company. Stephen Morgan Smith. No relation. People ask me that all the time. No relation. Wish it was. Was issued United States patent for an improved turbine water wheel on December 26, 1876. Smith had gathered ideas for those improvements through extensive discussions with local millwrights. The initial water wheels to Smith's design were sold in 1877. Launching what became the S. Morgan Smith Company. Smith possessed exceptional skills in marketing his turbine water wheels, resulting in strong sales from the start. He kept his capital expenses low by utilizing various machine shops throughout York to do the manufacturing. One of those shops was the York Manufacturing Company, which became York Corporation. It's now Johnson Controls, of which Smith was one of the founders in 1874. He resigned from that company in 1880 to focus on his company and the further development of his turbine water wheels. In 1890, Smith built his initial production facility at 500 Lincoln Street in the West End of York, as he begins to do his own manufacturing. S. Morgan Smith's oldest son, Charles Elmer Smith, followed his dad in going by his middle name. He graduated from the York County Academy and spent 2 years working in field engineering departments of the railroads out in the western United States, before returning and starting his career at the S. Morgan Smith Company in 1884. When the S. Morgan Smith Company was incorporated in 1896, C. Elmer Smith was appointed treasurer and general manager of the company. S. Morgan Smith's son, Stephen Falls Smith, also followed his dad in going by his middle name. He graduated from the York County Academy and immediately began his career at the S. Morgan Smith Company in 1885. When the S. Morgan Smith Company was incorporated in 1896, S. Falls Smith was appointed vice president of the company. Now, the S. Morgan Smith Company was innovative in pushing the idea of hydroelectric power by, on occasions, actually doing the hard legwork to get some of the earliest hydroelectric power plants approved and built. S. Morgan Smith obtained options on land and water rights to a site known as Bull Sluice on the Chattahoochee River, 12 miles north of Atlanta, Georgia. He envisioned S. Morgan Smith Company building a hydroelectric plant. They're not just supplying turbines, they're building the plant. If the site proved agreeable to such an undertaking. He sent his son, S. Falls Smith, to assess the site in December 1898. One landowner who granted an option was having second thoughts and on trumped-up charges had S. Fall Smith arrested. Of his trial the following month, quoting the Atlanta Constitution's newspaper report of January 21st, 1899, quote, S. Fall Smith of the firm S. Morgan Smith Company, wealthy manufacturers of York, PA, was arrested at the insistence of Taylor on the charge of conspiracy, and he was exonerated. So this trial, he was exonerated. But they went on to say, it is not often, therefore, that Judge Bloodworth has such distinguished pleaders in his court, or a case of such importance. S. Morgan Smith, who was at the hearing yesterday, is a Southerner, having been born near Salem, North Carolina. He owns extensive properties in the South, and is one of the best-known capitalists in his section of the country. End quote. Sounds like S. Morgan Smith really played up his Southern origins. It is probably good that the opposing counsel had no idea that S. Morgan Smith was a chaplain in the Union Army. So it's kind of a neat story that I kind of flushed out that I thought it was very interesting. The thing is, the arrest and trial actually brought people together, the lawyers for both sides, that actually greased the skids in getting the project going. So the arrest is actually beneficial to get the power plant built. The relationships forged there was very beneficial. So this is the power plant under construction. It commenced in 1902. S. Morgan Smith was the principal investor. Also, George Westinghouse was an investor. So you got George Westinghouse, and his lead engineer was Tesla. So they were in good company there. But basically, building the power plant, the S. Morgan Smith companies oversaw construction of the power plant. Now, unfortunately, S. Morgan Smith passed away April 19th, 1903, Easter Sunday. He never lived to see the power plant completed. However, the site was renamed Morgan Falls in his honor. Morgan Falls' first unit was placed in commercial operation on October 10th, 1904. Now, on this, you can see the 7 S. Morgan Smith turbines on this side. These are the 7 Westinghouse generators on this side. They were horizontal shaft units. The turbines were 48-inch diameter, Francis-type turbines, and I'll explain Francis-type turbines a little bit later, each rated at 2,000 horsepower. On occasions, during the 117 years this hydroelectric plant has supplied electricity, and is still supplying electricity, to the power grid, units are shut down for maintenance and runner upgrades. American Hydro in York County has done several of the turbine upgrades at this plant. The National Park Service manages the Chattahoochee River National Recreational Area adjacent to Morgan Falls. When units are shut down for maintenance, the Park Service offers tours to show the inner workings of this historic hydroelectric plant. At the top, note a service hatch is open on the scroll casing, allowing viewing of the inner workings of the turbine. So you see this guy up here looking in this hatch, you can see the inner workings of the turbine. So but that's kind of a neat tour if it happens to be open when you're down there. Now, following the death of S. Morgan Smith in 1903, for the next 6 decades, the company grew impressively in the capable hands of his direct descendants. S. Morgan's son, C. Elmer Smith, became the 2nd president of the company, and with one of his prime tasks was completing Morgan Falls, which opened the following year. S. Fall Smith remained vice president of the company. The Smith brothers focused on growing the manufacturing capabilities of their factory so they could produce even larger turbines being designed by their engineering department to meet the projected needs of the rapidly expanding hydroelectric industry. After Morgan Falls hydroelectric plant went into operation, C. Elmer Smith surveyed additional places in Georgia to construct another hydroelectric plant. Again, they're building their own plant, not just supplying the turbines. This time, nobody was arrested. Tallulah Gorge was the selected site. It was located 100 miles north of Atlanta. It was essentially a miniature version of the Grand Canyon of Colorado and could offer lessons learned to the S. Morgan Smith Company when larger hydroelectric plants would be built in the West. The Tallulah River cut through a deep gorge 2 miles long. The work was constructing a high dam at the head of the gorge, as shown, which was located upstream of Tallulah Falls. The powerhouse was placed in a gorge downstream of Tallulah Falls. A 1.25 mile long tunnel through solid rock and another 1/4 mile of petstocks deliver the water from the top of the dam to the powerhouse below the base of the falls, resulting in a working head of 580 feet, making it the highest head hydroelectric plant east of the Rocky Mountains. The 60-inch diameter steel petstocks supplies each of the 6 turbines in the powerhouse with water at roughly 250 pounds pressure. This is a view on the turbine floor of the powerhouse at Tallulah Falls, showing one of the Smith Francis turbines. It's a horizontal turbine, vertical shaft, with a 56 diameter runner. The pressurized water flows into the turbine scroll from the back wall. So it comes in, this is a 60-inch diameter pipe back here, coming in and supplying the turbine runner, which is located on this shaft out of sight. These mechanisms basically control the gates, which regulate the flow of water into the runner. The turbine connects via this 14-inch diameter shaft to a General Electric turbine, which is located on the floor above. The initial unit was placed into operation September 23rd, 1913. At 17,000 horsepower, this single turbine produced more horsepower than all 7 turbines in the Morgan Falls hydroelectric plant from a decade earlier, which shows the rapid pace in developing and applying hydroelectric turbines. This is a plaque at Tallulah Falls. I use it because, like Morgan Falls hydroelectric plant, the Tallulah Falls plant required constructing a railroad to get the heavily bulky equipment to the plant, because this is a very rural area. The railroads continued to serve communities through which they passed. The Morgan Falls Railroad was only 10 miles, but this particular one was 100 miles. So the communities along the path basically developed because of this railroad. So they not only developed hydroelectric plant, but developing a railroad which served a lot of communities. The hydroelectric power plants, along with the railroad, were grouped into a corporation known as the Georgia Railway and Power Company, of which C. Elmer Smith was the president and a longtime board of directors member. The 5th of the 6 turbines at this power plant was placed in service in 1914. The 6th and final one would have to wait until the end of World War I. A person sent me this probably about a year ago, and I did a little bit of research on it. It's kind of an interesting story. This is a large bronze plaque. It was found in a basement in Easton, Pennsylvania. There were a number of them. There were about 4 of them, I think, found. They were left over from something, and they couldn't quite figure out what it was left over from. I said, well, what was around here? They had some newspaper, they were wrapped in newspapers, and they were from the 1920s. So I figured there must have been something to do with World War I. And lo and behold, with World War I breaking out in 1914, even though the United States remained neutral through April of 1917, the Bethlehem Steel Company realized how ill-prepared the United States was if it entered the war. In October of 1914, Bethlehem Steel began planning upgrades to their plants, recognizing the future involvement of the United States in the war was practically unavoidable. One of their plans was to have the best equipped plant in the world for the manufacture of guns from 1-inch to 20-inch bore. The Bethlehem Steel engineers designed modern large gun boring lathes, and in their search for a firm to manufacture them, discovered the machining capabilities of the Smart & Smith Company. In order for the manufacture of 2 modern, Bethlehem Steel ordered from S. Morgan Smith Company 2 modern gun boring lathes. Bethlehem was pleased with the attention to detail, accuracy, and the workmanship, such that they ordered additional items. Now, this order was placed in 1915. This was 2 years before the United States entered the war, or well before the government was issuing contracts to people. So this was a contract issued by Bethlehem Steel. They wanted to get basically ahead of the game in supplying parts to the eventual involvement by the United States. These large gun turning lathes, in order to manufacture the 2 modern lathes to Bethlehem's design, basically they, get lost my place there. Okay, there it is. In the summer of 1915, the government placed an order on Bethlehem Steel Company for 20 16-inch bore guns. That was the initial order by the government. Realizing this was the first of many future orders, Bethlehem planned ahead and contracted with the S. Morgan Smith Company to manufacture 9 units, each containing rough and finished gun boring lathes and associated tooling to produce up to 20-inch bore guns. Remember, on the battleships, big battleships, they have 17-inch guns. So they were producing equipment to make up to 20-inch. So the S. Morgan Smith delivered ahead of schedule. It took 18 freight cars to transport each of the 9 units. They were, 90% of their output during the war was war-related munition work. And this photo shows a gun boring lathe room in a government ordnance plant to give a perspective of size. I pointed out arrows to some of the workmen in that photo. So these were big machines. As the United States entered World War I, the S. Morgan Smith Company also began to receive orders directly from the government. They got a license from Bethlehem Steel to produce guns to their designs. So S. Morgan Smith was using the Bethlehem Steel design, producing guns, and they supplied much of the equipment to the Neville Allen Armory or ordnance plant near Pittsburgh. And even after the war ended, the government has S. Morgan Smith complete the order. So they were producing stuff up through the 1920s. Now, in 1921, the first S. Morgan Smith Company hydraulic laboratory was built along Linden Avenue at the northwest corner of the plant. It contained a single open flume where new model turbine tests could be conducted under closer observation. Before, they were using private labs, which catered to the whole turbine industry. And in doing so, you basically, any confidential data was, it was supposed to be protected, but often it wasn't. So Smith was one of the first ones to develop their own hydraulic lab. That hydraulic lab would be expanded a number of times to the east and south sides. This photo was taken sometime after 1956 expansion, which features a high head turbine test facility and additional facilities to test their line of Roto Valves. In 1974, the hydraulic lab along Linden Avenue was shut down after Alice Chalmers opened a new $1 million, 4-story hydraulic testing facility north of the East Berlin Road plant. That new facility was dedicated as the S. Morgan Smith Memorial Hydraulic Laboratory. So they were still honoring S. Morgan Smith, even the successor companies. These are small scale models of various turbine configurations which were tested at the Linden Avenue Hydraulic Lab. It's from an S. Morgan Smith publication. Now, these are Francis-type turbines. Now, the Francis turbine was developed by James Francis in 1849. It remains the most common water turbine type used today. Francis never patented his design. Instead, he published the concept and mathematical principles which define his design. Many of the turbines produced afterwards followed the Francis design basics, and some improvements were unique enough, usually to the Blade Runners, to obtain individual turbine patents. Such was the case for S. Morgan Smith and some of the other people that contain patents for improvements to the turbine. Now, this Francis turbine drawing is characterized by radial inflow. So you basically have radial inlet flow coming into the turbine runner. And the runner is the thing that runs or rotates. So you have this part rotating, the shaft rotating to turn the generator up here. The purpose of the gates is to control the flow into the turbine. A draft tube is used to convert some of the kinetic energy of the discharge water back into pressure energy. So coming out here in the look. So you basically have axial flow going out, and the design of this actually impacts the efficiency of the machine. Now, the gates around the runner, when turned, they increase or decrease the blockage of water flowing into the runner, which controls the amount of speed that it's operating at. This is a bottom view of a Francis turbine, and they're still used today. This is actually a current publication from Voith Hydro. So this shows the bottom of our Francis turbine. So if you see the bottom side, this is what you'll normally see. This turbine contains 13 blades. Now, another type of turbine is the propeller turbine. Here the flow passes through the gates radially inward. However, the flow is axial through the runner. Axial meaning in the direction of the axis of the shaft. So it actually flows through this way rather than going into the turbine. This one, you actually flow radially into part of the runner, and then it goes out axially. This is the main difference between the two types. This is a propeller type, and it goes actually through the runner. Now, Dr. Victor Kaplan of Vienna, Austria, developed a variation of the propeller turbine in which the pitch angle of the blades are movable. However, the key part of his invention was having the movement of the gates work in concert with the pitch setting of the blades to maintain maximum efficiency over a wide range of head pressure, water flow, and load. On his invention, Kaplan filed a European patent in 1913 and a United States patent in 1914. However, due to World War I, no practical use of the design occurred until the early 1920s. As the design started to catch on in Europe, C. Elmer Smith became convinced it represented a real advance in the turbine industry. So, in the summer of 1927, C. Elmer Smith sent his brother, S. Foss Smith, to Austria to negotiate and bring back an exclusive Kaplan turbine license for the S. Morgan Smith Company. Joining his uncle on this trip to Austria is the initial third generation member of the Smith family employed by the company. Beecham Smith, the son of C. Elmer Smith, is a 1923 graduate of Cornell University with a degree in mechanical engineering. Out of college, he worked 2 years as a field engineer for the Georgia Railway and Power Company, owned by his father, before joining the S. Morgan Smith Company full-time in 1925. The trip to Europe was a success, with the final documents signed in 1928 granting S. Morgan Smith Company exclusive rights under the Kaplan patents for their manufacture in the United States and Canada. Then, the innovations of this type of turbine began. The S. Morgan Smith Company utilized their hydraulic lab to test the designs that they got from Kaplan. They incorporated years of experience that they had in turbine design and applied them to a slight revision to the design. They included extensive testing on the upper shape of the top plate, which is this plate here, to direct the flow the best it can do as far as getting axial streamline flow into the runner. So they did a lot of testing, not just on the Kaplan patents, but they did a lot of testing on other innovations. The first Smith-Kaplan turbine made in America was installed at York Haven, just up the river here, York County. So we have basically two connections here to York County. It's like it was made in York County and it was applied in York County. The turbine shown here is 93 inches in diameter runner. It was placed in service April 5th of 1929. For being the first Kaplan turbine produced in the United States for the innovations by its manufacturer, S. Morgan Smith Company, this turbine was recognized as a National Historic Mechanical Engineering Landmark by the American Society of Mechanical Engineers. It was the 53rd such landmark designated, so honored. The Safe Harbor Dam also contains Smith-Kaplan turbines. The S. Morgan Smith Company produced turbines for units 2, 4, and 6. And one of their Kaplan sub-licensees, I.P. Moore's Company of Philadelphia, produced turbines to the Smith design for units 1, 3, and 5. And the reason this was done, they wanted to build this dam powerhouse from putting in the Cobber Dam to having it up and running in 1 year and 9 months. And they did that. So they had to break up who produced them to get it done. And actually, S. Morgan Smith Company licensed 3 different companies to produce Smith-Kaplan patents to their design. This and the next 2 photos basically are shop views of the Smith-Kaplan turbine equipment manufactured for safe harbor. Here is the runner for the 42,500 horsepower turbine. This is the bottom view of the runner. It is 18 feet 4 inches in diameter. It also shows part of the blade moving mechanism. So this is part of the blade moving mechanism here. I'll have a cross section later that shows it a little bit more in detail. Good. Here the runner is mounted on the turbine shaft with the blade moving servo mechanism shown at the left side. So this is the mechanism that is required to move these blades, turn the blades one way or the other. Large specialty valves were produced by the S. Morgan Smith Company just for their turbine installations in the earliest years of the 20th century. However, by 1930s, the next generation of these valves were also offered to customers as a separate product line. Roto Valves was their trade name. This photo shows the shop assembly of a 42-inch roto valve, meaning the inlet and outlet of the valve at the left and right. So these inlets and outlets here and over here are 42 inches in diameter. Now, this valve was designed as a water control device using the concept of a conical stopper plug combined with the innovative sealing and controlling method that they devised. Just as turbines produced by the S. Morgan Smith Company continually got larger, so did the roto valves. This Gazette Daily photo shows Don Rensel, valve department foreman at S. Morgan Smith Company, standing next to a roto valve weighing 210,000 pounds. I've zoomed in on Don because he gets lost in the lower left of the whole photo. Big valve. Shown here is an 84-inch roto valve that Don Rensel is standing next to. It is one of 3 identical valves manufactured in 1953 for the government of Afghanistan for an irrigation project. It can be shipped because it breaks down into 4 sections. Now, although these valves were designed for water use, these roto valves found wide acceptance in various applications that they were really never designed for, but they seem to be well suited for. They're using sewage systems, water systems, and air systems. In one of the most demanding applications, 15 roto valves, just a little smaller than this, are used in 2 ballistic test tunnels at Aberdeen Proving Grounds to control the air pressure in the tunnels when they're being tested. The valve's positive sealing against air pressure plus speed of closure made them the practical choice for the job rather than designing something specifically for that application. And these basically proved themselves and they're still being used down there. Now, C. Elmer Smith passed away in 1936. His brother, S. Fall Smith, became the 3rd president of the company. The major projects during his tenure were completing the company's largest hydroelectric project to date and seeing that the factory had the machinery it needed to produce even larger turbines. So they're always making bigger and bigger machinery or purchasing it to make bigger and bigger turbines. Beecham Smith became vice president and general manager of the company. During this time, Beecham displayed far-sighted leadership in widening the field of products produced, one of which included developing controllable pitch ship propellers for the United States Navy. The initial association with the Navy had far-reaching impacts. So the association with the Navy actually began with this project in 1939. And it carried beyond the Smith organization through Alice Chalmers' ownership and continues to this day with the components that Precision Components supplies to the Navy. Now, from 1937 to 1942, 10 280-inch diameter Kaplan turbines were designed and manufactured by the S. Morgan Smith Company for the Bonneville hydroelectric plant developed by the Army Corps of Engineers on the Columbia River in the northwestern part of the United States. At the time, these were the highest powered Kaplan turbines in the world, each producing 74,500 horsepower, which is 25 times the horsepower produced by the York Haven Kaplan turbine, only 9 years earlier. So 25 times greater than what they produced 9 years earlier. This is a cross-section of the Bonneville powerhouse, pointing out the water flow through it. If one tours powerhouses, one usually sees the turbines floor up here. You don't see everything going on down here. It's buried in all the concrete. So you have the dam up here, the water flows in through the gates here, through the turbine, and then out this way on the downflow side of the river. Now, the gates here are special designed here because they're basically buried half in the concrete. Their lower bearings are in the concrete. So they use a lot of concrete scrolls here as opposed to the metal scrolls that a lot of the dams had. So there are a lot of innovations in this and a lot of innovations in the turbine. So I'll focus on the turbine here. Now, this particular cross-section was in a publication that George Jessup did in 1938. He was the chief engineer at the S. Morgan Smith Company at that time. He presented a technical paper at the spring 1938 meeting of the American Society of Mechanical Engineers, in which he describes many innovations introduced into their Kaplan turbines for the Bonneville project. So they consider this as the turbine that had the most innovations to it. In the interest of time, I'll mention just one. For the Bonneville turbines, they used far more fabricated parts as opposed to cast parts than they used in any other turbines in their history. It went so well, well, to describe fabricated parts, it means you're taking welded steel plate and welding it together to produce the parts. You're forming it and welding it together. What Smith did with this, it worked out so well that the foundry located in the north part of the S. Morgan Smith plant was substantially reduced and turned into a new welding and fabricating shop. A few photos of the gates and runners from the Smith Kaplan turbine at Bonneville follow. So this one shows gates in the shop being fitted up. The lower side here, these represent the gates. Look. These represent the gates here. Again, they're fabricated. Up here is the control mechanism to turn the gates open or closed. This looks into the pit where the runner would be located. So the runner basically drops in here. They basically set the gates into their bearings in the concrete. and then the upper control part gets on top of that. And you can kind of see, look down into the bottom of the pit here. They basically have a platform there so you don't fall into the water down below. And this is kind of a staged photo. I can't imagine the people sitting on those curved blades because it's about a 100-foot drop to concrete below. So this was definitely a stage photo that the Army Corps of Engineers used in a lot of their publications. But the turbine there is basically the, let's see, could be some personnel from S. Morgan Smith. None of the people are identified. It'd be nice to have an identity on some of them. Another thing that they did in Bonneville, again, they went to fabricated blades on the turbines, runners. And by using fabricated steel blades, they developed a method to profile it. So they basically had a wood pattern here on the, whoops, the wrong one. Okay, you have a wood pattern up here, which is well defines the profile of the blade. And you basically have a person up here basically move. That's the only woman I was able to find in any of the photos of the S. Morgan Smith company. You have a woman up here basically tracing over the wood pattern, and that directs movement of a machine tool down here to machine the surface of the blade. So that's how they did the, before computer-aided manufacturing, this is how you did it, to have all the blades the same size, or the same profile on the blade. Another thing that Smith did is, because the machine sizes that you could buy weren't big enough for them, so they would actually design their own machinery and actually fabricate part of it that they could there, and then they sent some of the elements out. But this is their 40-foot vertical boring mill. Again, they designed this machine, and because they couldn't find anybody that would sell them any that big to produce their bigger turbines. 40 foot means you can produce a 40-foot diameter part in here, turn a 40-foot diameter part between the legs here. They have some that goes up to like 65 feet now, I think. And you kind of see the relative size. I point to the man here over here, so you can see the relative size of the equipment that are machining there. Now, during June of 1940, the York Plan was hatched in the offices of the Manufacturers Association of York. In that plan, information was collected on all idle machinery and available labor to operate that machinery. The cooperative pooling of hours available on idle machinery allowed York businesses to successfully land large contracts that they otherwise would not have had the resources to bid on. All using the principle, do what you can with what you have. During World War II, S. Morgan Smith Company continued to produce hydraulic turbines because hydraulic power plants and the energy they produced was deemed as critical to the war effort. Because as additional factories were being geared up to produce mass amount of military equipment, they needed electricity. So all the orders that they had for hydroelectric plants still went on during World War II, and they actually produced additional plants, hydro turbine plants, in addition to their war effort, that the war materials they produced. Because the Smith plant also was a subcontractor to a lot of York area businesses to produce parts that they were producing on war contracts. Now, the S. Morgan Smith Company was a prime contractor, shown here on carriages for their 8-inch guns and 240 millimeter howitzer. So basically, they produced the carriages down here. A government ordnance plant supplied the gun barrel, probably machined on tooling they produced during World War I, and the recoil mechanism was produced by another manufacturer. So they basically assembled them here, and that was one of the things they showcased at the York Fair. They had the display of the various munitions that various plants produce. So this is a sign from one of their, and they basically had the carry trigger. They didn't have the whole gun there. Now, S. Falls Smith passed away in 1942. His nephew, Beecham Smith, became the 4th president of the company and the first 3rd generation member of the Smith family to lead the company, bearing the name of his grandfather. Burwell Smith, the son of S. Falls Smith, became the vice president of the company. Burwell had started working for the company as a hydraulic engineer in 1928. He did that immediately after graduating from Princeton University. Now, until the United States entry into World War II, a government-operated shop constructed the few new airplane catapults needed each year. Each required some custom fit-ups because the drawings really weren't set up for mass production. However, in 1942, after the United States entered the war, they're setting up a system where they're producing 40 new aircraft carriers every year. Most of them were known as escort carriers. About 122 of them were produced during the war. They were half the size of a normal aircraft carrier, so they needed a catapult to launch the planes under most conditions, unless it was really windy out. So they needed 40 new catapults each year. The Navy was not set up to do that in their small shop. And they were reluctant to turn this over to industry, but they quickly realized they had no choice. Now, as background as to why Smith plant got the job, in the late 1930s, S. Morgan Smith Company, General Motors, and Baldwin Lima Hamilton Corporation were 3 firms competing to develop a controllable pitch ship propeller for the United States Navy. So this program started in the late 1930s. All had distinctly different design approaches. Smith proposed a variation of their pitch control for the Kaplan turbine. GM proposed a mechanical jack screw arrangement. Baldwin proposed an electromechanical approach. The records show that the GM and Baldwin designs suffered numerous failures during the Navy testing. The Smith design performed, although it did not quite meet the full range of the design specifications. While Smith was revising their design, the Navy canceled the whole controllable pitch project, although it would be reactivated during the war. Now, the Navy contacts that Beecham Smith made via that program appears to be the reason that S. Morgan Smith Company was selected to try and qualify as the prime contractor for manufacturing hydraulic pneumatic catapults for aircraft carriers. Not only did they qualify, but the first unit impressed them so much that they got the job to produce all of them. And they even created drawings with accurate machining tolerances so they could use interchangeable parts. So they got the job, and they actually produced these catapults through 1954, well after the war. In 1954, the steam catapults, which are still used today, were introduced by another company. Now, the catapult, this is a kind of a drawing of the catapult system that S. Morgan Smith Company produced. The drawings that were turned over were known as the Type H Mark II catapult. The drawings that Smith created with better tolerances became the Type H Mark II Mod 1 catapult, this is a drawing for it. So the planes would basically be launched on the deck, attached to the cable that ran along the deck here. Underneath the deck was this control equipment, and describing the control equipment kind of shows a man at the controls. This is a view of the underdeck section, which uses compressed air as the power medium and fluid as the power transmitting agent. The fluid is a water-based, non-flammable liquid used for the application. And the basic concept of this catapult is a compound pulley system operated in reverse. I could go into a big explanation, but with time, I'll do that. Now, one thing that there is a Navy training film from 1944 that shows above deck and below deck tasks, and I had that in my latest York Pass post. I'll link to that. Now, for each airplane launched, the tailhook holdback unit is fitted with a new tension ring. The ring is a safety device. It requires the pull of sufficient full throttle from the airplane plus maximum tension from the catapult fairing to break the ring, which releases the holdback unit and safely launches the plane. So if you don't have either of those, the ring won't break and the plane won't launch. So, but the thing is, S. Morgan Smith Company produced all the tension rings for firing all the planes. So they produced large quantities of these tension rings, which had to be held to extremely close tolerances because they basically, for every 100 that were made, they tested 2 from the batch, and they had to fall within a particular go, no-go type test. If they didn't pass, all of them would be thrown out, and then the next batch, they'd be testing 10 of them. So you really had to be, there were a lot of quality controls on those rings. Now, another thing, there's a set of photos back in the archives here that labels these products unknown product. It has we probably have about 30 photographs of this type of device. It's unknown product. Well, I found out what it was. In August of 1944, NACA, which is the National Advisory Committee for Aeronautics, issued a study on the theory behind the type of axial flow compressor needed to power a high-speed wind tunnel for conducting advanced aeronautical research. Remember, this is still during the war. It turned out to be a very large compressor, a machine seemingly impossible to go ahead with. However, in 1945, as a result of the naval aviation catapult manufacturing, the NACA discovered the S. Morgan Smith Company had very large machinery to construct such a compressor. And they learned of the company's engineering know-how via the wind turbine project, which Steve Nicholas will be writing about. So the S. Morgan Smith Company was given the task of creating the drawings for such a large axial flow compressor so it could be produced. The drawings were completed and the compressor was ready to be assembled when Japan surrendered. Further testing on this product was canceled at that time. However, 1952, the NACA got the go-ahead to build an even higher speed, that is supersonic wind tunnel, at the Lewis Flight Propulsion Laboratory in Cleveland. The initial axial flow compressor designed by S. Morgan Smith Company was scaled up to produce the desired airflow. This photo shows one component of the larger compressor. This is the rotor going through final machining on the 42-foot boring mill at the Smith plant. I point to the men up here, and you'll see the relative size. So you see the men up here. So this is a big thing. Each one of these is an individual forging produced by Bethlehem Steel. It was a built-up rotor. And they built it up because there's a way that they had to basically sandwiched the blade sections on this. And the blade sections are shown in the next one. So this is the rotor here, and these are the blade sections, and then you see men standing all in between the blades inspecting them. So this is a big machine. The compressor blades assemblies were produced by CL Rocker Company in Kent, Ohio, and assembled to the rotor on the job site. The axial flow compressor was capable of generating Mach 2.5 airflow in the test section of the wind tunnel. That is 2.5 times the speed of sound, or about 2,000 miles per hour. In the photo, the stationary blades are clamshelled here. So these are the stationary blades that get put together on either side of the rotating blades to generate the airflow needed to power this machine, power the wind tunnel. This is one test section configuration of the NACA Supersonic wind tunnel. It became fully operational in 1956. It would be used by military and private industry over the years for stability test of airplanes and rockets in supersonic flight. Now, on October 1st of 1958, NACA was dissolved, and its assets, facilities, and personnel were transferred to the newly created National Aeronautics and Space Administration, NASA. So S. Morgan Smith Company had a hand in creating an early, heavily utilized test facility for NASA. The S. Morgan Smith Company also was involved in machinery to controllably move water at high speed through a water tunnel test facility. The Garfield Thomas Water Tunnel was dedicated in 1949 on the campus of Penn State. It was designed and built in cooperation with the Navy to test for torpedoes, submarine hull shapes, and propeller designs. It's named for Garfield Thomas, who is here. He is one of the earliest naval officers killed in action during World War II. He was actually a journalism major at Penn State. Now, early results of the Navy's controllable pitch ship propeller program, which was reactivated following World War II, shows an adjustable pitch design coupled with speed control on the drive motors could provide the full range of water flow characteristics desired for operating the high-speed water tunnel. S. Morgan Smith Company got the job of designing and producing the 95-inch diameter, 4-blade, adjustable pitch impeller shown at the lower left. The yellow arrows show where it was installed in the water tunnel. And this is from a drawing from S. Morgan Smith publication. Now, this is an example of the type of test being done in the water tunnel. Actually, S. Morgan Smith utilized this facility for some of their Kaplan turbines to cut down on cavitation. And this is an example of what cavitation is. It basically, when a propeller turns at certain speeds or certain designs, it produces bubbles on the surface, and because water is flowing from left to right, it produces this helix design. Now these bubbles create noise if you're in a submarine that you don't want, and at the point where the bubbles form can cause pitting. So there's two things you don't want in a propeller or a turbine design. You don't want cavitation. Now, so the reason you do these type of tests, you can visually see where the bubbles are forming, and you can use that to help redesign the propeller to eliminate this problem. Among the largest turbines ever built were a 1950s order for 14 Smith Kaplan turbines at McNary Dam hydroelectric plant on the Columbia River. Each turbine assembly is more than 100 feet high and weighs 1,000 tons. Smith was cramped for space in their factory in the West End of York, and the decision was made to build an additional plant for welding, forming, and assembling large turbines. This is a 1953 aerial view of the south side of that plant along East Berlin Road in West Manchester Township. To finance the $3 million construction, the Smith family sold shares in the company for the first time. They gave up about 25% ownership of the S. Morgan Smith Company to public shareholders. So for the first time, the Smith family didn't own the whole company. They had 25% ownership was private shareholders. Now, it's interesting now that basically this is the East Berlin Road. They have buildings up here now, and this has been substantially expanded a couple times when Boyd Hybrid has been there. Now, this is a view of a Smith shop assembly, scroll assembly on June 1st of 1955. Specifically, this is Unit 3 scroll of 4 Smith turbines for Palisades Dam hydroelectric plant on the Snake River in Idaho. As an example of updated manufacturing methods implemented during the 1950s, this scroll casing was produced to ASME Section 9. Now, Section 9 of the ASME Boiler and Pressure Vessel Code relates to qualification of welders and the procedures they employ in welding. This particular scroll casing also required X-ray checking of the welds. Now, producing product to ASME Section 9 would be a requirement for the upcoming nuclear Navy work that the Smith plant, Allis-Chalmers, and Precision Components would enjoy and still do. So essentially, this is kind of a neat view. You can see how large these things are because you can see the office here in the background or the step ladder going up the side. So if you know, this is probably at least 20 feet high. So these are big things.
You guys see a ladder there.
Yeah. Yeah, you can see the ladder down there. That gives you some perceptive size. I don't see any individual in this one. A lot of times they have individuals to show how big their units are. Now, the reactivation of the Navy's controllable pitch ship propeller program had Smith in the early apparent lead in competing against 4 new rivals for the production contract. The Smith Company would deliver 5 prototype propellers between 1947 and 1957, each with an improvement to the pitch control mechanism from the previous prototype. The control mechanism ended up in the propeller hub for the final 2 iterations. And basically the report that I've seen, basically they have propellers installed in Navy tugs, Navy mine sweepers. One was installed in a submarine, and then 2 others were moved around from various ship to ship. And they also ran through the Navy labs, all of them did. I could not locate any photos of the controllable pitch Navy work, which is probably usual. However, this photo shows a 210-inch diameter controllable pitch ship propeller in the Navy plant, which was produced in 1956 for the United States Maritime Commissions. They had a Liberty ship conversion program, which they were testing out new engines and new propellers. So this particular one was This is a shop floor photo of one of their big propellers that they were working on outside of the Navy program. Now, the production contract for the Navy's controllable pitch ship propeller was ultimately awarded to Bird Johnson Company in Massachusetts. And actually, Bird Johnson Company still produces controllable pitch propellers for the Navy. So, unfortunately, they lost this work. So, however, some of Smith's research and development expenses for the Navy's controllable pitch ship propeller program was recouped by producing a commercial product, the SMS controllable pitch ship propeller. These illustrations are from a June 1956 SMS ad in the trade publication Marine Engineering. In the late 1950s, S. Morgan Smith Company ads in trade publications utilize a new logo with SMS trade name underneath the S. Morgan Smith Company. So you see this, this basically a lot, and they note their products, and it's SMS Hydrodynamics, or S. Morgan Smith Hydrodynamics, and they note hydraulic turbines, pumps, rotor valves, ball valves, butterfly valves, gates and hoists, trash brakes, etc. These are all utilized in hydroelectric plants, free discharge valves, controllable pitch ship propellers. So this is a new product that they launched. At the time of this ad, this is I think 2 years after they introduced it, they had ship propellers in 86 vessels, which they state is more than any other domestic manufacturer. After Alice Chalmers took over, I think this product, this line was discontinued or they sold it. I couldn't find anything about that in the Alice Chalmers time frame. So with no Smith family successors wanting to take on leadership positions in the company, from Beecham and his cousin Burwell, a sale to competitor Alice Chalmers was put to a vote by the shareholders of the company on January 19, 1959. 93% of the shareholders voted in favor of the resolution authorizing the transfer of S. Morgan Smith Company's properties, assets, and business and intellectual property to Milwaukee-based Alice Chalmers in exchange for 1.1 shares of Alice Chalmers common stock for each share of Smith capital stock. The York Works of the hydraulic division of Alice Chalmers includes the original plant in the West End of York and the East Berlin Road plant. Beecham Smith continues to lead the local operations as Vice President of Alice Chalmers and General Manager of the York Works. Burwell Smith was named Assistant General Manager of the York Works and placed in charge of sales for the entire hydraulic division. Now, at the end of the direct involvement of the company, of the Smith family, is actually December 31st of 1961, when both Beecham and Burwell retire from Alice Chalmers. So the end of the Smith involvement in the company ends December 31st, 1961. Now, I use this timeline of the various companies to describe the various offshoots of the S. Morgan Smith Company. The red line here is the involvement of Alice Chalmers. And the red line, basically, I use that because in the declining, or in the early 1980s, the hydraulic division of Alice Chalmers had 3 successive years in the red. So they were losing money. And that's one of the reasons why they sold off their business at the plant in York, which was the then known as the Nuclear Components Division of Allis-Chalmers. Basically, they produced a lot of vessels for the nuclear navy and commercial nuclear facilities. And so that was the prime part of their business. And they sold that off in 1983 to a bunch of local, a group of local investors, which renamed the company Precision Custom Components. That corporation branches down as the gray line here. And then in 1995, Precision Calibration and Testing branched off from that, which does a lot of X-ray testing of welds and calibration of delicate equipment needed at various companies. Yes?
Are all these separately owned, or are they still owned?
Yeah, they're all separately owned. Yeah.
Do they still have correlation with each other, or are they completely?
Well, actually, the Precision Calibration and Testing, I understand that they do work with both Voith and American Hydro, which are two separate companies. Yeah.
They're competitors.
Yeah, they're competitors.
American Hydro and Voith actually compete on bids for the same projects.
Right.
Yeah, my stepdad worked there back in the 70s.
And they're the only two companies in the whole country.
Right. That still do this, yeah.
They're American owned.
Yeah.
Yeah. Right.
Well, no. Voith is German.
It's German, yeah.
That's better than Chinese.
Yeah.
But
Yeah. So in the beginning of 1985,
My stepdad worked
yeah.
there. He was a supervisor.
So in the beginning of 1985, the newly appointed general manager of York's Hydroelectric Division of Allis-Chalmers is tasked with quickly turning that unit in West Manchester Township into a profitable company. And he did, and they did. He assembled a team of him and three engineers that they basically streamlined operations, and they made changes to the way that they bid, and they landed some major projects, and that division became profitable. However, in 1986, Allis-Chalmers was on the verge of bankruptcy, and they did declare bankruptcy the next year. So in 1986, they sold their hydro turbine division to German hydroelectric manufacturer Voith. Voith Hydro, designated by the green line here, they still operate in York County and they still produce product, but like it's a German corporation that they have the North American plant here in York.
Did they keep all the employees and everybody?
Yeah, they still pretty much have most of their employees.
Oh, yeah, well, now that's 30 years ago.
Well, they've enlarged a number of times. Most of the work that hydroelectric work is basically repair work or upgrade work because there aren't a lot of new dams being built because of environmental concerns.
Are there any original S. Morgan Smith or Allis-Chalmers employees still working for any of these people anymore?
Yeah. Well, most of the people working there are actually, they worked at Allis-Chalmers. I haven't talked to any that actually worked at S. Morgan Smith. Because that's 1959. Yeah. So in Alice, because of the four engineers that did the turnaround for Allis-Chalmers, they were a little upset that basically it was being sold to Voith, so they decided to create their own company. And it was basically, there's four engineers in a business kind of incubator. They had two offices and a secretary, so that's the start of American Hydro. And they basically built it up into a substantial sized company out in Springersbury Township. So they are, like Steve said, they are the two companies in the United States that still produce basically components for hydroelectric plants, turbines, the upgrades. Both are in York County, so that's kind of neat. And they both kind of, well, you have a direct descendant by Voith and an indirect descendant by American Hydro. But essentially, to finish up my talk, the S. Morgan Smith Company was a family business in York County for over 80 years. Led by three generations, the company produced products utilized throughout the world. The leaders of the company also had a significant impact on the well-being of the York community. You can read about all their involvement in the York community in Steve's book. I would say well done. Any questions?
They still have those plants, the S. Morgan Smith, Lincoln Street, that's still there, right?
Yeah, that's Precision Components
They're
now.
still rolling.
Yeah, they
Still
still,
rolling too.
yeah, they still do a lot of nuclear work. I think as of the last, I guess 2 years ago, I saw an article, they did a lot of the nuclear components for the aircraft carrier Gerald Ford. So they're still doing a lot of nuclear work there. And they're surprisingly, like I think starting in like 1985, the U.S. Navy retires about 4 submarines every year. And when you retire a nuclear submarine, you basically have to cut out the nuclear part of it, put it in a containment vessel, and those containment vessels are built by Precision Components, and they're shipped to an area out in Washington State that they're buried in the ground, and about 1,000 years from now, they'll be okay to open them up.
No, about 10,000.
Well, they're saying 1,000, but yeah.
I had a question.
Yeah.
In the Hoover Dam, I was told that the turbines were built by S. Morgan Smith for that. I didn't really talk about it. Is that wrong?
I'm not sure if Hoover Dam was one of their. I know they had the Grand Coulee Dam out there. I never saw
My
Hoover.
remark, the first dam that he made, the first turbines he made in Georgia,
Yeah.
he died before it was done.
Yes.
But you heard what he said?
Yeah.
They're still running. They don't
Oh
wear
yeah.
out.
Yeah, they're still running. Yeah.
They don't wear out.
Well, they haven't been upgraded. American Hydro actually upgraded some of those.
Right.
Yeah, they upgraded. Yeah.
Right.
But there are turbines that they typically run like 70, 80 years, that then they need an upgrade. The bearings, a lot of the bearings are Kingsbury bearings that you can run forever, but there are parts in there that do wear out with the continual beating of the water into them, and they do have some pitting issues that you try to design it out, but occasionally you have problems. Parts go through. You have screens there to prevent rubbish from going through, but it goes through, so it creates problems. But 70 years is a pretty good life for a piece of equipment. Yeah.
I think I remember this, but my memory isn't as good as it used to be. I think I read that when they built the Bonneville Dam, the turbines were too big to ship out. And they actually built a plant out there to assemble them. Do you know anything?
Oh yes, they've done that all the time on really big ones. That they actually have an assembly plant at the site to put them back together. So
They manufacture them here.
Yeah, but they sent the parts out.
they sent it out in pieces, yeah. And they've done that a number of times. Even on this one for this air compressor, that went out into I think like 20 train cars 3 different times to send the parts out to Ohio to build that. And they assemble it out there because it's too big to ship.
He also made garbage cans to put nuclear waste in.
Oh yeah, yeah.
I had never looked at that.
Yeah.
So what they do, they made parts and then modern printing press made parts.
Yeah.
And they go out in the middle of the ocean and drop them in with that radioactive waste.
Yeah.
And then we don't remove the
But modern printing press could say the same thing. The printing presses that were built by modern printing press in 1956 are still running.
Oh yeah.
It says a lot about York.
Yeah.
Is that where you took your trade?
Huh?
Didn't you take your trade with modern?
I took my trade with I took my trade with Live and Slidehorn.
Oh,
But as soon as I finished, I went to Modern for 20 years.
yeah, I was going to say, I thought you did from modern.
That's
Yeah.
interesting.
Any other S. Morgan Smith comments? Not. We'll break up, and I'll be here if you have any other questions. So thank you.